Push That Rock here with Simpson Math. In this video, I want to explain fractional exponents and give us an example of a function that uses fractional exponents that I just stole out of a biology textbook. So this function here is y is the basal metabolic rate. Ask a biologist what that is. I think it has something to do with how we use energy or how we transform energy when we're resting, I think is what basal means. And the units here are milliliters of oxygen per hour. And X is the weight of some primate. So the data came from 25 species of primates in grams. It turns out that if you know the weight of the primate, you can plug it in right here and you'll get out the metabolic basal rate of that primate species. So the input is the weight in grams, the output is this metabolic weight. But what does this exponent 3/4 mean? That's what we want to talk about in this video. And I'll use a biology metaphor to help us. So we're all familiar with a tree. And I ask you, where are the roots of the tree? That's correct. The roots are in the bottom under the ground. And then we have the leaves up here. And as we all know, the leaves are green, and that's because they have chlorophyll in them, and that's because they use sunlight. That chlorophyll helps them take the sunlight and turn it into energy. So the leaves provide power for the tree. And we're going to use this little metaphor to help us understand fractional exponents. So a fractional exponent is something like this. So we have an exponent, here's the base, and here's the exponent, sometimes called the power. We sometimes conflate the term exponent and power to mean the same thing, but actually power is the output here. But we don't have to be technical. So this is the exponent or power, and this is the base. And we want to know, what does this fractional exponent mean? And we're going to use our biology metaphor. It turns out that one of these numbers is a power or exponent, and the other one is a root. And you guessed it, the root is the one in the bottom. So 3 is the root. So we're taking the third root of 8, and then we are raising that to the second power. So you leave, here's the leaves up top, you just leave the leaves up top. You leave the power up top where the leaves go. So it stays up there. Now, oh, y'all can't see that. So I took the root, put it here, the thing in the bottom, the number in the bottom is the root. The number in the top is the power, and it stays where the leaves are in the top, okay? Now, this is, I could have written it this way as well. They're equivalent. So the square can go here, the power of 2 can go here or out there. In this case, it's easier to take the cubed root of 8 and then square. So I'm going to do that. I'm going to do it in that order. The cubed root of 8 is 2, because 2 times 2 times 2 is equal to 8. So since 2 times 2 times 2 is equal to 8, we have two facts. We have 2 to the 3 equals 8, but we have the cubed root of 8 is equal to 2. Okay? So when I took the cubed root of 8, I got 2. And then next I will square it, and I will get 4. Okay? So let's take our example from biology. So our example from biology says, where should I put it? Oh, let's just put it over here on my drawing of a chalkboard, okay? That if we have some primate weight, we can put it into the function. I don't know what primates weigh, but I'm gonna pick a convenient value. So I'm gonna pick, let's say there's a primate out there that weighs 16 grams. Is there one? 16 grams seems kind of small. Maybe, well, there's some small primates, I guess. So pretend there's a primate that weighs 16 grams. That means I'm gonna put in 16 as my input and find out its metabolic rate in milliliters of oxygen per hour. So this means that I have the fourth root, of 16, because the 4 is in the bottom, so it's where the roots are, raised to the third power. So I have 2.63. The fourth root is 16, that would be 2, because 4 2's multiplied together give you 16. And I raise it to the third power. Oh, I need to magically extend my whiteboard. I'll pretend that this whiteboard in this drawing is like my whiteboard that I'm currently using and has an infinite number of space, because you can just keep scrolling, okay? All right, so 2 to the 3 is 8. So I have 2.63 times 8. Now I must point out here, I'm following the rule of order of operations. You have to finish the exponent before you can multiply. Students frequently try to multiply this number, especially if it's a nice easy number like 2 or 3. You'll go, oh, 3 times 2 is 6, and then try to raise it to the third power. You'll get the wrong answer. You have to follow the rule of order of operations. Exponents first, then multiply. But now that I've finished taking care of the exponent, now I can multiply. So I just have to multiply 8 by 2. Let's see, that'll give me 16. And then 8 times 60 cents. Let's see, 8 times 6, is that 48? So that's 8 times 60 cents would be $4.80. And then 8 times 3 cents would be 24 cents. So when I add $4.80 to 24 cents, I get $5.04. And you add that to 16, you get $20.04. But this is not dollars. I was just using that to help me do the math. What this is the metabolic rate of the primate that weighs 16 grams. So if you have a primate that weighs 16 grams, its metabolic rate is predicted to be basically 20 milliliters of oxygen per hour. Math made simple, Simpson math.